the little buttons wiggling, and it's on. So, okay, we're recording our session. I'll post it on Moodle later. All right, first thing to say, of course, is that finally I got my act together. Somebody helped me out. My Moodle expertise is getting better, but still not where it should be, I guess. And somehow I had some misplaced Moodle activities, but they're all where they should be now. I don't want to tell you what I did wrong. It was pretty typical of me, I would say. But in any event, finally, part of our test 2 is posted on Moodle. It will be open till Sunday at 11:30. So whatever, from today till Sunday, you have to do it. There's really no time limit on it. You can just do it. When you open it. It doesn't say you have a limited time to complete it. I don't know what that means if you're halfway done. I don't know any of that, but so please go to Moodle, look for T2 Activity 2, and click on that and answer the questions with regard to what we've been discussing about electricity and electrical phenomena, and a little bit of the related subject of gravity and gravity phenomena is covered in that T2 Activity 2. Now, what I also did on Moodle in the grade book was I gave you my incentive points. Remember, we got a deal. The deal is that the second test is 100 points. There's 40 points on there now for you to do. There will be 40 points next week for you to do. And then I throw in the other 20 points because I'm just such a great guy. So I put the 20 points on for test 2. What that means is it says on your test 2 grade that everybody has 100% right now. Don't be fooled by that, because your contribution will be 80 points of that will come when you complete this T2 Activity 2 and the T2 Activity 3 that we will do later next week or whatever when I get it posted, and hopefully I won't screw this one up. Okay, so that's the story with that. Please make sure, don't wait till the last minute. It closes at 11:30 on Sunday. Nobody really wants to ruin their weekend by doing this on Sunday. If you explore through the slides and look closely at the things we talked about, the things we talked about are all covered in this activity with regard to electricity. The next one will have to do with ideas of magnetism, and that's where we are now, and a little bit about circuitry and things with regard to what the fun things that we do with electricity and magnetism to make our lives so much easier. So that'll be pretty much the subject of this week. So what I'm going to do now, of course, is I'm going to present, and when I do all that, I do a little bit of clicking here, and it tells me I can do those things. And hopefully now we are seeing where we ended up at the end of the period last time. And I'm going to go to the slide where we ended up. And we had ended up with a discussion of the weirdness of the Earth's magnetic field. And of course, there's a couple weird things, and I always like to recap a little bit. So I hate to bore those of you that pay very careful attention to what I say. But let me just do a brief recap of the highlights of some of the things we did discuss last time. The Earth has a magnetic field. I think we all know that. And it's actually the Earth's magnetic field that we use to designate the behavior of magnetism. If you have a north pole, it points towards the top of the Earth. So north magnetic poles would be what would happen if you had a polarizing magnetic material. Its needle would line up so that it would be attracted towards the Arctic Circle of the Earth. Now, I'm not going to say it's exactly at the top of the Earth, but it's up in the Arctic Circle somewhere. A south pole would be attracted towards the Antarctic region of the Earth. So we designate, instead of plus and minus as we do with electricity, we designate north and south as the flavor of magnetic force. Now, again, why do you need two flavors of magnetic force? Just like we had to do with electricity, it is because the magnetic phenomenon is either repulsive or attractive, like the electric phenomenon is either repulsive or attractive. Uh, in contrast, the gravitational phenomenon is only attractive, period. So that's why we don't have to have plus or minus mass. We only need one kind of mass because all masses are attractive toward one another. There's no repulsive gravitational force. All right, so the Earth has this magnetic field, and we talked a little bit about its origin. Its origin is because the center of the Earth is still incredibly hot from the origins of our solar system. The Earth has cooled to the point where the outer crust has solidified over the billions of years the Earth has existed, but the center of it is still liquid and incredibly hot, incredibly hot. It's so hot that the material that makes up the Earth is not only melted, but there's so much heat that electrons are allowed to move freely off of the molten element iron in the center of the Earth. So the molten iron in the center of the Earth is charged. There are currents of motion, like incredibly fast-moving rivers of charged iron in the center of the Earth. Charge in motion creates a magnet. So the center of the Earth is a huge magnetic field. Now, as you go outward from the center of the Earth, and remember, there's about 10 to the 6th meters to get to the center of the Earth is cooled and cooled and cooled, and it's solidified. And of course, the magnetic field of the Earth falls off as you move away from this center of motion of charge. But the inner solid component of the Earth has been exposed to a very intense magnetic field from this location for billions of years. So iron rocks that are near the center of the Earth have been exposed to this intense magnetic field for so long that they are permanently polarized. So there are permanent magnetic rocks that have been exposed to this intense magnetic field near the center. It's not nearly as intense out here, but it's still measurable very easily with a compass. But if volcanic eruptions bring those rocks from the center of the Earth to the surface of the Earth, humans have harvested them over the millennia, and we have had permanently magnetic rocks and permanent magnetic materials for thousands of years now. And we have fooled around with them for thousands of years and found applications for them over that period of time. Okay, so other things of great importance that the Earth's magnetic field provides are this phenomenon we talked about at the very end of our time together last Wednesday. That is the protection that the Earth's magnetic field provides from the so-called solar wind. The solar wind is an artifact of the fusion processes happening on the sun. There's so much incredible high energy smashing of hydrogen atoms together that they're forming helium and releasing incredible amounts of energy. Also, incredible amounts of other ionized matter is coming out of the sun. And so it's belching streams of highly charged particles through the solar system. And because the Earth has a magnetic field, these charged particles, as they fly toward the Earth, create a magnet because they're charged. So they have a magnetic effect associated with them. And a large amount of this highly charged ionized matter flying from the sun is deflected by the Earth's magnetic field. So this protects the Earth from the bombardment of this kind of stream of possibly dangerous matter that could be impinging upon the Earth, that shield that has allowed life to flourish on Earth. Believe me, if the Earth had been bombarded with this highly ionized matter for the millennia, or actually for the billions of years that the Earth has been here, that it's really hard to estimate or even predict what changes that would have had in the evolutionary cycle of life on the Earth. There's a very delicate balance of the rules of nature that has produced the forms of life that we see on this planet at this time, upsetting the rules of nature even ever so slightly over expended periods of time. We'll have dramatic and drastic changes occurring in this delicate cycle of how life has evolved and changed and flourished, and what does flourish, what doesn't flourish, is all part of this massive equation of the yin and yang of what goes on this planet. And any slight variation of that can cause, over eons of time, can cause pretty substantial change in the outcome of this delicate process. So who knows how different things may have ended up occurring on this planet had the Earth's magnetic field not been able to shield this planet from this bombarding of this potentially dangerous solar wind. I can't even begin to tell you the combination of factors that make this planet so unique. Many of them is the atmosphere that it possesses of this incredibly reactive material, oxygen, the ridiculous amount of water that is present on this planet, which provides not only the theater or arena in which life can be developed and sustained, but also has physical properties of keeping the Earth from getting too hot or too cold from day to night. So the water on this Earth provides an incredible, if you like, shield and nurturing field for the development of life. The oxygen on this planet provides an incredible nurturing entity for the development of life on this Earth. The magnetic field of the Earth is a nurturing entity for the development of life on this Earth. So you have to have this incredible, amazing balance of factors that allow life to develop and sustain on a planet in the universe. So it's not surprising then that life is a rare occurrence in this universe. So the odds of having life developing on a planet are very, 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 very slim. But when you consider that there are over 10 to the 20 stars that we think exist in the universe, and all of those 10 to the 20 stars, uncounted numbers of them have orbiting satellites around them, the likelihood that there are not, again, somewhere out there, the replicated conditions that are favorable for the development of life, it's hard to believe that that's not possible. It really, truly is. I would be stunned if there is no other life in this universe. Now, how you define life and what it means to be alive, then that's something we could debate. But to think that there's not somewhere in the nooks and crannies of this vast universe in which we live the right conditions for this magic to have occurred is, I don't know, that's a little shallow, I think, in terms of your thinking. All right, so enough of my editorializing about what's going on in the universe. I wouldn't be surprised. I'm not going to claim that there's how many intelligent life forms or how many advanced life forms might be out there, but I find it hard to believe that there aren't any at all anywhere out there. Let's look at another phenomenon that results from this idea of streaming the charged radiation or charged matter from the sun away from the Earth. In particular, this stream of matter is deflected most effectively at the polar caps. And what this creates in the Arctic and Antarctic are what are known as the Northern Lights. Well, that would be what they're called in the Arctic. Maybe they'd be called the Southern Lights in the Antarctic. But we get these incredibly dazzling displays of color in the atmosphere, particularly in the evenings and at sunset times, where just incredible colors are displayed by the deflection of this charged matter through the sky and the polar caps in the Arctic Circle. And it's either called the Northern Lights or the Aurora Borealis. Okay, so let's now look at a charge-carrying wire. Now, we are going to have more to say about charge in motion in a conductor in our next little unit of study when we look at what electricity can do for us and how we can envision what electricity is. But let's just for the moment pretend there's some way in which we can generate a current. Again, later even this period, we will look at ways in which we can generate a current in a conductor. If you have a conductor that is carrying current, and current is charge in motion. So I have charge flowing through the wire. Now, maybe the first thing to note is the oddity of what the charge in motion will be. The physicists love to define these quantities relative to how the positive is moving, but the positive is never really moving. We might have to blame Ben Franklin for that. We do actually define current relative to the direction positive charge would move, but it turns out, as we have talked about several times, that positive charge is really hard to get moving because the electrons are much more mobile than the positive charges. Typically, we have negative charge in motion. So when electrical current is electrons, as the name implies, moving through the conducting atoms of the element that makes up the conductor. And as we will see here a little bit briefly in upcoming slides, there's some weirdness about the definition of the direction of a current flow. We'll deal with that when we come to it. Let's assume I have a wire that is pointing upward on the page as I show here. What will happen is a magnetic field, a emanating north and south pole coming off of this charge will be generated by the wire. So the wire naturally becomes a magnet. And being a magnet, it generates a field. And as we've talked about several times now, a field is action at a distance. The magnetic field provides a push or a pull on other magnets without touching them. So this field that is generated from the magnet, as you can see in the left picture, coils around the wire. So it kind of flows circularly around the wire. Now, what physicists have recognized is what is known as the right hand rule. If you take your right hand and you point the thumb of your right hand in the direction that the current is flowing, then the fingers of your right hand wrap around in the direction that the magnetic field wraps around the wire. So again, this is known as the right hand rule. If I have a wire with a current flowing toward my face, then I look at how my fingers are wrapping around that wire. You'll see they're curling around that wire in a counterclockwise form. Notice my thumb pointing towards my face. Then the fingers of my right hand are coming up on the right hand side and going down on the left hand side. That's opposite the direction of motion of the hands of a clock. So that would be moving counterclockwise. If I have current pointing towards away from me, we'll say. It's away from me. And look at what my fingers are doing as I point my thumb away from me. Now my fingers are curling clockwise around my thumb, coming up on the left-hand side and then going down on the right-hand side, just like the hands of a clock. So the magnetic field swirls around the wire as in the same manner in which your fingers curl around your palm when you point your thumb in a particular direction. So if I have current, and this is exactly what this is trying to show, I have current flowing. The dot means the current is coming towards me. I didn't give this definition yet, but I will in a moment. Capital I, is the symbol that physicists use for current. And that circle with a dot in the middle is trying to indicate that that's the tip of an arrow. So the current is flowing directly toward my face. When I do that, my thumb is pointing towards my face and my right hand fingers are moving upward and then back down around, or in a counterclockwise fashion around that wire. Now, typically physicists, as you see at the bottom there, they use a symbol capital B, and the little hat on the top of the capital B is saying that that is the direction of the magnetic field. So the field lines are flowing circularly counterclockwise above and below this wire coming with current coming towards me. If I turn the wire sideways, okay, now I've turned it sideways, so the current is going this way. At the top of the wire, my fingers of my hand are looking me right in the eye. And when the lines are coming towards you, that is a north pole. Remember, on earlier slides, if we back up to what we discussed on Wednesday, magnetic field lines are designed so that they come out of a north and go into a south. So if I have a current flowing to the right of the page, above that thumb, my fingers are pointing towards my face. Coming out at the top means north, and then if I curl my fingers around, it's a little weird, underneath my thumb, my fingers are curled so that they're pointing away from me. Going away from you field lines means south. So when the current is flowing to the right, the top part of the wire is like a north pole. The bottom part of the wire is like a south pole. Now, this is then interesting if you start putting two wires next to each other. And the power company or electronics makers have to concern themselves with this. And I'll say in a moment what they do to keep this phenomenon at bay. If you have two current carrying wires, as I do on the bottom left of the screen, they both have a current I, and again, we're going to make that a more clear definition later, but I is what physicists use to represent the current, and the current is flowing to the right on the top wire and the right on the bottom wire. Once again, if I look at what my fingers are doing, with my thumb pointing to the right, above each wire, my fingers are looking me right in the face. Current comes out of a north, so the north is on top of both those wires. If I let my fingers wrap around underneath the wire, my fingers are going away from me under the wire. So those are souths at the bottom of both of these wires. And when I put them in proximity so that I stack one wire on top of the other, you'll notice that the top wire underneath it is a south-looking pole. The bottom wire above it is a north-looking pole. So what would naturally then happen is that these two wires exert magnetic force of attraction upon one another. The top wire attracts the bottom wire attracts the top wire. That's what the two arrows to the left of the wires, the red arrows, are trying to show. The red arrows are showing the attractive force that current carrying wires that have current moving in the same direction will experience due to the location of the poles of the magnets that are created for those wires. Now then, guess what would happen if instead of having the currents flowing in the same direction, I have the currents in the wires flowing in opposite directions? The top wire has current still flowing to the right, just like the two wires on the other side of the bottom of the screen do, but the bottom wire now has a reverse current. And again, I can play my game with my fingers. I put my thumb now pointing to the left. My fingers above my thumb are pointing away from my face. Field lines going away or south. So above the wire with current going to the left is the south pole. Let them curl around and let's look at what the left pointing current field looks like under the wire. As I wrap around my right hand, now I'm looking at the tips of my fingers under my thumb. So under the current, the field lines are coming out. Field lines coming out mean north. So under the wire is a north pole if the current is heading to the left. But now when I put this wire in proximity to a wire with current flowing right instead of left, you will now notice that the south poles of the induced magnets due to the current flow are in connection to one another. Like poles repel, just like charges repel. So these two wires would exert repulsive force on one another. And the red arrows to the left of them indicate that the top wire is being pushed upward, the bottom wire is being pushed downward due to the results of this behavior. Okay, now what electronics engineers have learned is that they could use a trick to make electronic devices avoid this problem. I talked with you briefly about how they would do that. Maybe it was on Wednesday, maybe it was on Monday. I really can't remember which it was, but I talked about it. I called that a Faraday cage. If you surround a wire with a conductor, there is no field inside the conductor. So you can shield the inside from any field effects by wrapping a conductor around the outside of it. I call that a coaxial cable. It has a conductor around its outside, typically, and then it has a real straight, pointy little wire with a kind of a metal male-female connection thing that you twist and turn together when you connect coaxial cables to one another. It's not all current carrying wire in that, only the center middle wire, the little stiff straight one coming out, is the current carrying wire that you're putting together when you twist them together. The outside of it is wire, but that is not current carrying wire. It's just conductor used to shield the inside wire from any external effects because of what happens when the external conductor is impinged on by outside fields. Okay, so that's the end of the story for those particular slides. Of course, that's not the end of the story entirely. I have some other slides here that I want to turn to. What did I do? Oh, there they are. What we're now going to do is we're going to look at some phenomena that result from the weirdness of this magnetic behavior. And there are many applications that humans have figured out because of these effects that of attraction that magnets have for one another, the effects that opposite charges have electrically on one another. And most importantly, the effect which occurs when you move charge to create a magnet. So remember, we should definitely keep this in mind. If you have stationary charge, then the stationary charge exerts what we call electrostatic force. And I'm sure you have often heard of the term static electricity. When we mean static electricity, we mean the charges are sitting still. And when they're sitting still, they can have plus repelling other pluses, they can have minus repelling other minuses, or they can have attraction between plus and minus. That's static electricity. Once charge begins moving, you can still have plus repelling plus, minus repelling minus, and plus attracting plus. Yes, moving charge can still do that. But now there is a completely new phenomenon in the mix. Completely new. Charge in motion creates magnet. So now not only can you have pluses and minuses playing a game of push or pull with one another, you can now have north and south of the motion of the charge, providing an additional attraction or repulsion. So once charge starts moving, not only is plus and minus force in play, but also north and south attraction or repulsion is in play. So we talked a little bit about the nature of what this ultimately means. You can make materials magnetized because the elements such as iron have lots of electrons in them. Those electrons have what we call spinning motion of charge. I described spinning motion of charge in great detail on Wednesday. Tune into that if you want to see what I said about electrons spinning and how spinning electrons create magnets. So certain materials, particularly there's a few what we call ferromagnetic materials, have a lot of this spinning electron motion, and they can be used to create permanent magnets. In particular, the three most popular are cobalt, nickel, and the most popular being iron. There are a couple others as well, but those are certainly far and away the most common permanent magnets that we have in nature. Okay, so what I want to do is start these slides up and talk about some of the effects that this magnetic and electrical phenomenon led to. Let's start with a very interesting thing that occurred a long time ago, as you can see, 200 years ago, in 1820. That's a long time ago, 200 years ago. Things were quite different 200 years ago. In many regards, of course, technologically, we were quite different. Now, I think I've had this philosophical discussion with you before, but I have to do it again because that's the way I am. I'm very repetitive. I certainly do not believe that humans are more intelligent now than we were in 1820. I don't believe that at all. I certainly think there were just as many smart people on the planet in 1820 as there are in 2020. What I do believe is that our knowledge base is so much greater in 2020 than it was in 1820. You have the benefit of living in what I would call the age of information. And I'm sure 1,000 years from now, when historians look back at this particular time, they will call it the age of information. There was the Stone Age and the Iron Age and the Bronze Age and the Industrial Revolution. I'm pretty convinced that historians will look back on this as the age of information. And what do I mean by that? Communication and understanding has been hypersensitized. I would like you to stop to think about in 1820, if you wanted to communicate an incredibly important discovery between Europe and America. It literally took the quickest communication would take 2 weeks for people to find out something that happened in Europe in 1820. Why? We didn't even have telegraph. Well, they were beginning to get telegraphs. They were beginning to note that they could send electrical signals by 1840, 1850. They could do it by then. But they still couldn't send them across the Atlantic till probably 1870 or 1880. So it took a lot. Someone literally had to hand carry the information on a ship. It took 2 weeks to get the message from London to New York. So there was an incredible lag in understanding. And besides that, yes, of course, there were great centers of learning, great libraries available. You could go to these libraries and find reference material if you wished to discuss or discover information about a particular subject. But you had to be able to go to one of these institutions where these centers of learning were available. You had to go to the major cities and major centers of knowledge to be able to access information. You, of course, even I have figured out that I can access pretty much any information I want instantaneously with this thing I have in my hand. And the ability of humans to communicate, share information, share important events in this instantaneous sense has literally accelerated the entirety of the technological phenomenon. Things that took hundreds or decades of time to develop, now through the sharing of information, the sharing of technology, we're having this incredible acceleration of the time it takes for us to advance and progress. Progression has accelerated by an incredible rate due to all these advancements. It's really, what I would say is probably if you lived in 1720, the difference between 1720 to 1820, there was some definite improvement in life by 1820 compared to 1720, no doubt. But pretty much for most people from 1720 to 1820, things were pretty much the same. I would say from 1620 to 1720, things were pretty much the same. But if you contrast what humans had available in 1820 compared to 1920, things were different. Communication was different, transportation was different, all sorts of things like that were way different. If you compare what things were like from 1920 to 2020, everything is different. Everything. And of course, even you guys probably won't be around. Who knows what changes might occur. But in 2120, you can only imagine if we still have not killed each other off or destroyed our planet entirely. It's hard to fathom what things might be like by 2120. There's no doubt about that. So there's this incredible acceleration of technology. Again, I must reiterate, do I think humans are smarter now than they were then? No. Do I think humans are going to be smarter in 2120 than they are now? No. Now, let's not get into the philosophical or sociological aspects of the changes that occur in terms of our openness and our more acceptance. And that's not quite what I'm getting at. But I'm just getting at our raw intelligence level. I think certainly people were just as smart, uh, 100 years ago as we, or even 200 years ago as we are today. And okay, enough of that philosophizing about the nature of intelligence and uh, are we really more intelligent than we have ever been? Let's now turn to this guy, Hans Christian Ørsted, who was a Danish physicist in the 1820s. And what he was doing in particular at this time was giving a public demonstration. He was a Danish physicist. He was in Copenhagen, and he was doing a theater performance. Now, I have to point out to you that this was quite common at the time. Back in the early 1800s, entertainment choices were fairly limited. Now, believe me, there were huge urban centers in the 1820s. Every country pretty much had a huge urban center by that point in time. And of course, if there were choices for entertainment, they would certainly be in the urban centers. But the choices of entertainment in the urban centers probably at this time were limited to some dining options, a little bit of dining options, a theater, probably one theater option, maybe an opera option. Uh, and that's probably about the limit. There was sport okay, there was some rudimentary sport that you could attend, I'm sure, at that particular time, but nothing like the options of entertainment that we have now. So one of the main urban sources of entertainment was smart guys opening up a lecture hall and showing the wonders of the world. So this was not only common in Copenhagen, it was common in Italy, it was common in France, common in Germany, common in England. In the urban centers, the brilliant scientists of the time would perform. They would rent out a lecture hall, bring some wizardry and wonder, and demonstrate the wizardry and wonder, the latest advances in scientific uh, progression, and then give some sorts of explanation about what they were showing. And Hans Christian Ørsted was a person doing such things. And as he was doing a demonstration in Copenhagen in 1820, he was on stage and he has a circuit with a battery. So he was doing some wizardry with batteries, showing what you can do with electricity. He also had some magnets and he had a bunch of compasses. And what he noticed was when he connected his battery circuit, the compasses that were laying on the desk all jumped. The needles on the compasses all jumped towards the circuit briefly, just for a fraction of a second. And if he left the current hooked up, the needles quit jumping. If he disconnected the circuit, the second he disconnected the circuit, the needles jumped. But then they quit jumping and they went back to pointing north. So he has 20 compasses laying on the table. All their needles are pointing north when he doesn't put the current on. As soon as he connects his DC, I'll say what that means in a moment. He connects his battery circuit, the needles all jump, but just for a second. And he just stood there in front of this, audience of a few hundred people or whatever he was doing. And he just kept doing this over and over again, amazing himself. And he noticed when he moved the compasses around, the needles would deflect in different ways. But they always returned back to pointing north after a very brief second. He'd move them all the same side. They'd all point the same way. Move them all the top. They'd all point the same way. They spread them around. They all point inwards in different directions. And word has it that he got so distracted that the audience got really upset with him because he was only doing this and just saying, what the heck is going on? Why are these needles dancing the second I connect the circuit, but then they quit dancing? So being a scientist, he communicated what he discovered to other colleagues. And the conclusion that was drawn was that he was changing a current generates a magnet. So as a current changes, a magnet is generated temporarily upon that action. So what a contemporary of his named Michael Faraday, who also got famous watching these shows from smart people demonstrating behavior to an audience. That's how he got his start, doing the same sort of thing. He was doing his in England compared to Ørsted doing his in Denmark. But Faraday found out what Ørsted was doing, and he set out to see if you could do this in reverse, because he could recognize immediately the importance of doing what he wanted to see if he could do. If he took a magnet, could he move magnets and make a current? Okay, so essentially what Ørsted was doing was moving current to make a magnet. Faraday wanted to move a magnet to make a current. And again, I can't overemphasize to you the importance of what Faraday decided he was doing. It became known as Faraday's law of induction. If you move magnets, you make current. Ørsted more or less is saying, if you change current, you make magnet. So this is Michael Faraday, a picture of him. I don't have a picture of Ørsted, but one of the reasons that Faraday is one of my heroes is because he did important contributions not only in physics, but he did them in chemistry as well. But most importantly, to my knowledge, Faraday is the last of the great self-trained scientists. Faraday, as you can see, lived in the early 1800s, was when he was doing his best stuff, but he never had a formal education, ever. He never went to university. Every great scientist, believe me, that I know of, maybe there's one or two that I'm just not aware of their academic backgrounds, but believe me, the university system was very well established by the 1700s. In case you don't know it, Harvard was established in the 1600s. The University of Georgia was opened in 1740. So universities have been around for a long time. And of course, when you get a pedigree in science and trained in science, you turn to a university to give you the background information that makes you, trains you to be a scientist. Faraday is the last individual I know of who basically taught himself stuff. And some of the stuff that he came up with, he was very clever. He was probably the original Edison. Edison came along not too much after this. Edison came along 50 years later than Faraday. But believe me, Faraday laid the groundwork for all the great things that Edison later was able to do. And one of the things, and this is kind of a cartoon trying to show you essentially what Faraday figured out. It's his experiment in magnetic induction. And what he did is he defined a two-circuit system. Now, a little bit later, probably on Wednesday, I'm going to show you more about circuits and the diagram of a circuit and what a circuit means. For us, essentially now, A circuit is a closed conducting loop. Now you'll notice on the left and right, there are two complete closed loops of wire. Now, the one on the left has a switch on its upward going side. On the left side of it, there's a switch. Then at the top of it, there's a plus and minus source of electrical difference that we call a battery. So that symbol at the top that has an E on top of it is generating a flow of electricity. It's got two plates or two terminals, as we will see are called, that have charge separated on them, and the charge wants to flow so that they become evenly charged, and it flows through that conductor it doesn't flow through the air between the plates. The flow of charge is facilitated through the material connecting the plus to the minus. So I connect the terminals of a battery with a conductor and I make a circuit. So this is an electrical circuit. The left one I'm calling the primary circuit, the right one I'm calling a secondary circuit. The primary circuit and secondary circuit are only connected by wrapping part of their wires around an iron bar. So at the bottom, the gray thing represents an iron connection between the two circuits. Nowhere in the primary or secondary are there wires actually connected to each other. They're just connected they're wrapped around the piece of iron. Now the iron, much like we saw with the electromagnet before, can have a magnetic field induced in it very easily. The atoms of iron in that bar polarize and make little internal magnets, and then the magnet generated in the primary can be converted over to the secondary through the magnetization of that gray bar that has wires from each circuit wrapped around it. So what happens is that there's no current in the secondary circuit as long as the current in the primary circuit is constant. So if the current just is flowing and flowing and flowing on the left, nothing happens on the right. But when you alter the current on the left by opening and closing that switch on the left, so if the primary's current fluctuates, as the current in the left fluctuates, there is induced a current in the right. So changing the current on the left turns out to induce a current on the right. So the question then is, what is going on when only the current in the left changes? Do you make a current in the right? And the answer is that changing the current in the left makes a magnet in the iron. So if we were to back up here, Ørsted had learned that if you change the current, you make a magnet. So here Faraday is on the left, changing the current, and it makes a magnet. That magnet transmits through the piece of iron to the secondary circuit. But it doesn't move electrons into the secondary circuit. What it moves is a magnet in the secondary circuit. So in the secondary circuit, he has a changing magnet, which makes a current. So one more time. On the left, I have a changing current, which makes a magnet. On the right, I have a changing magnet, which makes a changing current. So he's using these ideas to connect one to the other. Later, we will see that this is the heart of what we call a transformer. Transformers can either make the current greater or lower. They can make the voltage greater or lower, and they use tricks like this in order to pull that off. So Faraday is able to make and induce, as we call this magnetic induction. I'm inducing a current in the secondary circuit by changing a current in the primary circuit. Now, this might sound just like an academic exercise, meaning something that can be done, but really doesn't seem to have immediate utility. Well, let me tell you what. This Faraday induction is the secret to us getting any mechanical thing done from an electrical circuit. Now, what do I mean by that? Let's take probably the simplest mechanical transformation. Plug a fan into the wall and the blades spin. How do the blades spin? Well, quite simply, at the base of the fan of the magnet, there's a series of, at the base of the fan, the propeller blades are attached to a metal piece that has little magnets on it. And the little magnets are placed near a circuit that comes in from the wall to the region where those magnets are. When you turn the fan on, charge starts to move through the electrical circuit of the fan. The charge moving in the electrical circuit of the fan makes magnets, as we've talked about. The magnets have attractions or repulsions with the circuit magnet has attractions or repulsions to the fan base magnets. They either get pushed or pulled to that circuit as the charge, to that magnet of the circuit as the charge flows through it. So you start to drag the magnets and repel the magnets in the fan, and you make the fan blades spin. So this same basic idea is used anytime you have an electrical device that you plug in that becomes a mechanical device. That anything that moves an object up or down from an electrical circuit is ultimately doing so by spinning magnets being repelled or attracted from the electric field that is passing near those magnets. So it's the interplay of electricity and magnetism that makes it possible for us to harvest mechanical work energy from electrical stored energy in a circuit. So that alone is Faraday's probably greatest accomplishment. Now, ultimately, he didn't see the advancement that I'm talking about so much. It took, after his discovery, it took, till people like Edison took these ideas and ran with them and made a ridiculous number of useful devices using the tricks of Faraday, essentially. Okay, so what it boils down to is that Faraday's law of induction is also known as Lenz's law. And what Lenz's law says is a conductor which experiences a change in magnetic field or flux, change of the field lines, generates a current that tries to oppose the change. So here's what we should think of is what this Lenz guy is saying. There's a certain amount of electrical field that conductors experience. Maybe it's none, maybe it's some steady electric or steady magnetic field. So a conductor has steady magnetic field in it, whether it's none, whether it's huge, whether it's tiny. If you try to change whatever magnet is in it, the conductor says, I don't like that. I want everything to stay exactly the way it was. So if you lower the magnetic field in a conductor, the conductor makes its own magnetic field to replace what you removed. How does it do that? The charges in the conductor begin to run around to make a replacement magnetic field for what you've taken away. Or if you try to increase the magnetic field through a conductor, it says, wait a minute, you're putting too much magnet in me. I want only the magnetic field I've been experiencing in me. So I'm going to magically, now this is magically make electrons run around in me to make my own magnet, which will oppose your increase of magnet you're trying to force upon me. So in a neutral conductor with no electricity flow, with no current, with no nothing, you just have a piece of conducting metal. You put it in a magnetic field. As soon as you try to change that magnetic field, it says, wait a minute, you can't do that. I want it the same. So if you try to lower the field, it will make its own magnet by moving charge to put back the field that you're taking away. If you try to increase the field, it will move charge the other way. Why? Because it wants to make the opposite magnet to stop you from increasing the magnetic field it experiences. Magically, the material moves charge. What is charge moving? Well, it makes magnet, but charge moving also makes current. So materials can be induced to make current if you switch the magnets in them, if you switch magnets in them. So here's what smart people like James Fulton, James Watt, Thomas Edison, what they figured out. Let's make a steam-powered engine, which will move a magnet, and will move the magnet in a conductor. So I move the magnet in and out of a conductor. And as I move the magnet in and out of a conductor, like it's attached to the piston on an engine. As you move it in, you're increasing the magnetic field in the conductor. It makes a current in one direction to make magnets to stop you. When you pull it out, you're lowering the magnetic field that the conductor experiences. It makes current in the other direction to stop you from doing that. So part of the time it makes current in one direction, part of the time it makes current in the other direction. And it just does this at the speed and frequency at which you move and shove the magnet in and out of the conductor. This is what we call an alternating current that is being generated in the conductor as you move a magnet in and move a magnet out of the conductor. So that's what this cartoon is trying to show here. I have a loop, and the loop is a conductor, and it has north magnetic field lines coming out of the north pole of that magnet. If I shove the magnet into the loop, it makes a current that flows around and out of the loop. So I show an I at the top and an I at the bottom. So I'm showing what the X and the dot mean currents going in at the top and out of the bottom, which is not of consequence. The direction of the current's not of consequence, but what it is of consequence is that I'm making a current in the loop to oppose the change in magnetic field that the conducting loop experiences. So as you shove the magnet in, it makes the opposite magnet itself, so the current flows in at the top and out at the bottom. If I pull the North Pole away, I'm lowering the magnetic field in the loop. Now what you'll notice is I've switched the dot and the X from the top to the bottom, and I'm making a magnetic field to replace what I've taken out. So I will generate an electric current in one direction. Now, again, I don't care that we know which direction is which. If I push the magnet in, I make an electric current in the conductor in one direction. If I pull the magnet out, I make an electric current in the conductor in the other direction. Now you attach this to a steam engine, you do it in a power plant, you burn some coal, you burn some natural gas, even in a nuclear power plant, you make steam from the energy of nuclear fission, but in some way you make a mechanical device which will shove the magnet in and pull the magnet out, and shove the magnet in and pull the magnet out. The power company does this at a regular frequency, and they wrap the magnets with huge numbers of conducting loops of wire, and they harvest the moving charge that is inducing that magnetic effect, and they pipe it to your house. And they call it alternating current when they're doing this trick. Now, if I were to move the south poles, it's really the same kind of idea. I'm just showing that I would get the opposite effect. Remember, magnetic field lines go in on south. So if I pull the south pole magnet away, I got to replace that field. I'll make a current in one direction. If I shove the south pole in, then I will make a current in the other direction. I'll induce a field in the opposite sense. So it works whether I push a north pole in or a south. And when I'm really not so concerned that we know the direction of the current and the direction of the field that we make. But what I am concerned is that you note that when I'm pulling it in or pushing it out, I'm going to make the opposite current show up in the wire. This is why we have alternating current coming out of the wall. The power plants that we use generate alternating current mechanically by burning coal, shoving magnets around, and collecting and harvesting the electricity that comes out of such an action. Okay, now, what is electrical current? That's what the rest of these slides are really going to focus on. I is a symbol I've already been using for electrical current. So we're going to continue to use the symbol I. If you will remember a few slides back, I used Q to indicate charge. T, little t anyways, is an indication of time. And the little Greek triangle there is a delta. So I have delta Q over delta T. Now, what does delta mean to a physicist? It means change. So I have, for the current flowing through a conductor, the change in charge in the conductor divided by the change in time. So current is change in charge with change in time. So if I stand here with a stopwatch and I hit go, so time starts at TI, and when I hit it again, it stops at TF. That will be my delta T. Tick, TI, tick, TF. So I know my change in time. Then I count, I sit here with a little pad. I count how many charges run by me in that time. And I had better be able to count fast, because a whole bunch of charge is going to run by me. But let's just say mechanically, or using a computer, or in some detector, a voltmeter, a current meter, I can count the charge that flows by me in that unit of time. I count the change in charge going by and the change in time over which that charge went by, and that is defined to be the current. So current is change in charge with change in time. Okay, so the units of current take the units of charge divided by the units of time. So current has units of Coulomb per second. Now, more importantly to most people, we change that into a new name, the ampere or amp. 1 ampere is 1 Coulomb of charge passing you every second. Now, it turns out that's a lot of charge. An amp current is a pretty good amount of current. Now, don't get me wrong, your household current is certainly in amps, but I think you're probably also aware your house current is packing a lot of punch. Because if you stick your finger into your household current circuit, you're going to be hurting. So this is a fairly high amount of charge moving every second. What does this mean? Remember, the charge on each electron was about one, well, to make it easy, we'll make it 2 times 10 to the minus 19 coulombs. So again, the charge on every electron, not quite, but it's about 2 times 10 to the minus 19 coulombs. Okay, so if I want to get an amp of charge in a second, that would take 5 times 10 to the 18. Now, I'm a nerd, so I can do this in my head quick. Again, I don't expect you to do these kinds of things with the numbers. But what I will tell you is in 1 second to make 1 amp of charge, you would have to send 5 times 10 to the 18 electrons by you each second. That's 5 with 18 zeros. That many electrons go by you each second just to make 1 amp of current. Now, believe me, we have plenty of devices in our house that use over 2 amps. We have plenty of devices in our, not plenty, but we have devices in our house that will use 10 amps. So we are flowing lots of charge through these wires. Now, that's one reason why electricity is so dangerous. All this charge moving through conductors can cause a lot of friction in the wire. And friction in the wire can cause a lot of heat in the wire. And a lot of heat in the wire can cause fire. And there's many instances of electrical fires due to improper circuits trying to carry the electrical current that they can't carry. So we're going to be looking at things like that certainly upcoming here. Okay, so charge flowing through a closed conducting path, which returns to the starting point. Now, that you have to have, we call it a circuit. An electrical flow can only occur in a circuit. You have to connect the plus to the minus, and the charge tries to run away from the plus to make it to the minus. It won't go through the air to do that because the air is an insulator. It will travel through the conductor from the plus to the minus. So the plus has to be connected to the minus. This creates what we call a circuit. And what we're going to do over the course of the rest of this week is look at the ramifications of the electrical connection of a circuit and how we can use it to do all the wonderful things that make our lives so much simpler. Okay, so I'm going to call it there. Please remember, I put assignment number 1, make it activity 2 of test 2. Look for activity 2 of test 2 on Moodle. It will be available until 11:30 Sunday. It must be completed by 11:30 Sunday. So please make sure that you go out there and do that. And until next time, peace out.